Alrighty. So welcome everyone, and thank you for being here. The few of you really appreciate it. It means you care about your infrastructure, you care about testing, and most of it, you care about GPUs being too expensive. Uh, yes. So this talk is inspired on a project that I've been working on for the past couple of months, and it's really all about this title, is GPUs are hard to get, even for me that I work for NVIDIA. So every time I share this with people, they are surprised, but yes, getting access to GPUs is hard, even by working at NVIDIA. So uh, what had I done? I had to build my own test library so I can test and I can run my CI and I can move forward. Or if not, I have to be in a queue, in an email queue for weeks to get one-day access to a GPU. So GPUs are hard to get even for us. So it's not just you, it's everyone is having the same issue. So, and the hard part is for cloud native, every component of the Kubernetes stacks requires you to have a real GPU to test, or if not, you are basically blocked, right? So you need the NVIDIA driver, you need the device plugin or DRA driver, depending if you are new, you're using the new thing or the old, and you need the NVIDIA GPU operator to at least get your cluster ready so you can run GPU workloads. And all of this is because you need that black line there. You need the libnvidia-ml.so. Basically, you need that shared file that tells the applications, mostly Python applications in your pods, that there is a GPU outside of the container and it can be used. But so what if you can have a kind cluster that fakes all of that to the point that you can test your Python applications or your applications that use CUDA libraries without having a real GPU? What if you can do it in a GitHub action, for example, that is CPU only? So who am I? I work for NVIDIA, so it's also a problem at NVIDIA to not have access to GPUs. And I've been working in Kubernetes and containers since it was not fun, so for over 10 years now. And I'm here to talk to you about this project that I built that is called nvml-mock. And this is new, so it's the first time we talk about it. And we have now like the third release of this project, and I hope it's of use of you, and you will be able to integrate it into your CI pipeline or even into your reference architectures. But I want to kind of like do a small walkthrough on why this is so hard and why it took us a lot of work to get this done properly. So when you are mocking your GPU stack, you are doing it correctly and you are not just returning no-op calls. This is everything you need inside a pod, or everything you need to get your GPUs inside a pod, right? So for the kubelet to allocate a GPU, the device plugin or DRA driver in your cluster needs to be telling the Kubernetes cluster that there is a special device or a GPU that can be scheduled or allocated. For NVIDIA, mostly this happens through the GPU operator that does all the internal wiring. And what happens in the end is that the NVIDIA Container Toolkit creates a CDI file that it hands over to Containerd or Cryo, and then that tells the container shim in the kubelet what needs to be injected into your pod when your pod is running. And when your pod is running, this is everything your pod will or should be seeing internally. That are all your shared files, your CUDA drivers, and even your Linux files, right? So it's not just the NVIDIA drivers, that you need inside your container, things like /device, /proc, and many other things that are required for your CUDA applications to actually work. So in the black box there, you can see everything that you require inside your pod for any application that is using a GPU to actually work, right? So you need all the /dep files, you need the library mounted, you need hooks, you need the NVIDIA CTK hook, because if you need extra capabilities from your GPU, we will edit your CDI file, so you need that, and you also need environment variables to tell your applications where the shared libraries are. So all of that black box there is magic that happens for you given the container toolkit, the NVIDIA container toolkit. And it happens in this sequence, right? When the scheduler tests the device plugin or the array to allocate a GPU, they hand over the CDI file to the kubelet. Then this turns into injecting all of that, depending on container D or cryo. And then your application has access to the GPUs. For those that are not aware or are new to this, we now have DRA. So it's GA since two Kubernetes releases ago. The old way of requesting a GPU was nvidia.com/GPU. That didn't allow you to request a specific type of GPU if you had an heterogeneous cluster. With the new DRA, you can request the type of GPU and even the if you need a special memory size of GPU, if you need a special type of GPU, if you need a GPU with a special capability enabled, you can do that with DRA, which you were not able to do with device plugin. Device plugin was basically a raw string. So with DRA, we open the door to specific ways of requesting resources. For the NVIDIA case, the NVIDIA DRA driver has two resources that is exposing: GPUs, that is still on tech preview, and compute domains. Compute domains, that is what we have in GA right now, is a way for you to consume GB200 NVLink, right? So if you have a cluster with GB200 or GB300, with compute domains, you can allocate pods into a clique or kind of like a special set of nodes that are connected via NVLink. Or you can request GPUs to the cluster as you will do with device plugin. But it is still on tech preview because we are trying to do everything as you were doing it before with the device plugin. Everything is upstreamed and donated. So we donated the DRA driver to the CNCF. It is now under 6. So the Kubernetes 6 DRA driver NVIDIA GPU, although it has the NVIDIA word, it is open source and lives in the Kubernetes repos. So this is what a compute domain is. Doing this by hand is really hard, right? Getting a clique is an abstraction made by the NVLink team to tell which nodes are connected via NVLink. And you can have multiple cliques, meaning you can have multiple subset of nodes in a rack of a GB200 that are sharing NVLink, and then they will be isolated kind of like by network, kind of like to say this abstraction like this. But what we are doing with the compute domain is with this API internally, the NVIDIA DRA driver will create a virtual small clique, and then your pod is only going to see this subset of nodes, and then your running application will see all the GPUs in those subset of nodes, and it will be able to share memory across the GPUs that are in that subset, right? So that is the good thing about a compute domain, is that it allows you to do kind of like a gang scheduling in the same rack of a GB200. But in order to test that, as you might imagine, is a very complicated operation because it requires you to inject the IPs and the NVLink click ID information of every node into the pod. We need to fake and mock all of it, right? So I'm showing you here the stack. So all of this information needs to be exposed to the pod in order for the pod to be able to leverage an NVIDIA GB200 click, or we'll call it an IMEX domain, right? So if you don't have a GPU, they're not present, we need to fake everything, right? And that's what I'm here to tell you, and that's well, the name of the talk is fake it until you make it, right? So we need to fake the NVIDIA IMEX and Fabric. That cannot be mocked, right? In order to do this, we fake it by injecting files and injecting fake IPs via config maps. But everything else, we can mock it, right? So we created nvml-mock. It is ABI compatible with CUDA. It is ABI compatible with go-nvml. It has all the entry points of nvml, and it has 7 GPU profiles, requires 0 GPUs. nvml-mock is actually nvml file, right? So if you know, nvml is actually the libnvidia-ml.so. That is a shared file that tells your applications where all the CUDA files are and where the /dev files are. And we do this by generating from the CGO, that is actually the nvml that gets injected into your pod when you actually have a GPU. So we generate the same subset of libraries, but all of them are returning just a no-op call. We mock the engine and the configurable devices, so everything is mocked all the way to the libraries. So nvidia-smi, the NVIDIA device plugin, or NVIDIA DCGM, if you run them, they will actually think that there is a GPU in the host. And here is an example. If you deploy the nvml-mock and you run nvidia-smi, nvidia-smi actually thinks, and this screenshot is taken on my laptop. So my laptop running nvidia-smi thinks that it is a GB200 node. So we can mock everything in such a way that the original, because as I was showing here, the real binary of nvidia-smi thinks that there is a GB200 GPU in your laptop. And then by doing this, we can also configure. So you can select, just using environment variables, which type of GPU do you want, right? If you want to test a GB200, a GB300, A100, and we are trying to add more and more GPUs to the list. Hopefully, as soon as we get access to a beta Rubin, we will add beta Rubin to the list of GPUs that you can test via this profile. We are working on adding also metrics and alerts that you can fake. This is very important for those doing chaos engineering or also testing platform engineering that need to test when a GPU goes down, when an entire node or entire rack goes down. We are adding features to the nvml-mock in such a way that you can fake an XID event, you can fake that a node is unrecoverable, that a node is lost. So you will be able to manually test your architecture and test that a couple of nodes are gone. How is your architecture going to respond to this? Because we will have a dynamic way of faking errors into the NVIDIA stack. And this is also good because if you are tidying your alerts and metrics to the DCGM exporter, then you can test what happens when an error comes from DCGM all the way to your observability architecture. To mock the GB200 fabric, we had to get a bit creative because it is complicated to inject NVIDIA iMex into a pod in a fake way. So we defaulted by config maps. So we create a list of IPs as the iMex daemon will do in a real GPU. We first decide the IPs since we are faking it, and we inject that via config map to the pods. So by doing that, we basically have like plain files that are faking the IPs of your click. And then with that, we tell the internal NVIDIA iMex that we fake the binaries. So we fake the NVIDIA iMex binary and the NVIDIA iMex CTL binaries. So when your application is trying to use them, it will read the file that we're injecting via config map and tell your application that there is actually NVLink connection with another GPU. But everything is just being handled via config maps. And so far, we have tested with workers in kind, so we can deploy a kind cluster in a laptop and make it think that it is a GB200 that has iMex connections. We also fake the entire CUDA library, right? So if you run, for example, an application that we use internally at NVIDIA a lot, but it's an open source container that you can, if you look for CUDA sample in the GitHub repository, it's an open source, very small, I think it's a C++ application. It's called Vectorad. So we fake the entire CUDA library in such a way that when you run this container in a Kubernetes cluster, it actually runs and finish with 0, meaning the application, all the functions and all the calls that the application does to CUDA have an actual reply, and the application runs to completion. Then you can use this application to test your Kubernetes deployment if you are testing an architecture that You are testing an application that will run on a GPU. You are waiting for a GB200 to arrive, or you are waiting for that Amazon or Azure contract to be signed, so you get that allocated access to a GPU. While you wait, you can test it using this library. So once you get the real allocation, everything you did in the test is going to be valid, because all of these mock calls of functions are being verified against real CUDA libraries. Who is using it right now? Right now, the NVIDIA device plugin, the NVIDIA DRA driver, the NVIDIA GPU operator is using it. There is also a team inside Google that is using the nvml-mock to test their internal DRA drivers, not just for NVIDIA, but to test they are extending it to their TPUs, and they are doing a lot of fun things, mocking their infrastructure. So even at Google, they are having issues getting access to GPUs. And these are all the combinations of GPUs that are being used right now in real CI production scenarios using the nvml-mock libraries. So you can basically design your GPU-aware CI and run it. There are, with just these lines, you can run, for example, in a GitHub Actions, and that way you can run integration tests over a fake GPU, and then you don't need to get GPU GitHub Actions, for example. You can just fake it using this, and then you will save a lot of money. And also you will save time, because sometimes the GPU GitHub Actions are busy and you end up waiting for them. So if you mock your GPU, you don't need to wait and you don't need to spend the money. But also, a very interesting project is if you need a scale testing, right? So Run AI, they also have something that is called the fake GPU operator. So if you need to test not just the functionality of running your application in your architecture, right? That is what the nvml allows you to do. You can also mock scalability testing. So by deploying the fake GPU operator next with the nvml-mock project, Run AI team is testing fake 1,000 node Kubernetes cluster for testing things like scheduling, allocation, making decisions, reference architectures, testing their K scheduler, testing multiple configurations of their entire stack. And once they move from the tested architecture to a real architecture, it simply works, because all of this is being made in collaboration with the CUDA team and with the GPU operator team. So everything that we are mocking here is coming from the real projects in such a way that when you actually deploy it on a GPU node, is the same behavior. So I invite you all to use the fake GPU operator from the Run AI team. It is open source as well. I think I have the link. Yeah, the Run AI fake GPU operator. That's the name on GitHub. And everything I've shown here also is open source. So everything we are doing at NVIDIA for Kubernetes is open source. So the nvml-mock, it lives in the KS test infra. And all of the projects, the DRA now lives in the Kubernetes 6. So if you want to see it, it's already in Kubernetes 6. NVIDIA go-nvml, that's the real, not the mock, but that's the real bindings that we have from the C libraries of nvml into Go. So if you want to write things for Kubernetes, mostly it's Go-based. The NVIDIA device plugin, that is the old school. Now the new school is the DRA driver. And the NVIDIA toolkit, that is what actually does the actual magic of creating the CDI files and injecting them into your pod. So I was trying to be really fast here. So CPUs are scarce, are really hard to get, and now you have a tool, a real tool and an open source tool that can allow you to run your CI jobs without an actual GPU. And hopefully Beta Rubin will be coming soon to this fake library, so you can test Beta Rubin while you wait to get your Beta Rubin. So thank you. Questions? We have plenty of minutes. If not, you can find me in the hallway. Questions? It's basically on a kind cluster. So you create a kind cluster and you deploy it, and your kind cluster, it's a Helm chart, so everything gets mocked there. Yeah, so it's purely kind based. So you can do it. We went for kind because kind is very lightweight, and you can. There is a lot of people that use kind, for example, on GitHub Actions, and one of the main reasons for this library is for CI. So yeah, you basically need a kind cluster, and you deploy the Helm chart, and you get it. So yeah, kind cluster is the way to go. So workload, we try to use the vector add because we know it's a CUDA application that we have been maintaining for a long time. It's very small. The name vector add is just like adding matrices basically, but it tests all the functions of a CUDA library, and it tests all the functions of a real GPU, right? So that's why it's kind of like our to-go application for testing it. But I know the Run AI team is deploying other applications. Like what I do is the CUDA vector add, but since your Kubernetes cluster thinks that there is a GPU and that you have multiple GPUs, you can deploy other workloads. Some may fail because I am only mocking all the library calls that the CUDA vector add does. So if your application does a CUDA call that is not in the CUDA vector add application, so nothing will be there and it will then fail, right? But if so, please clear an issue and I will fake that library for you. There's no problem. But the workload that I'm faking right now is the CUDA vector add. But the good thing is that it allows, CUDA vector add is enough to test if your entire reference architecture works. Like if your applications can reach the GPU operator, if when you deploy your architecture, you can schedule a pod into a specific node, you can test everything. Is that don't try to deploy very complex CUDA applications because some of the libraries are not going to be there. No, no, because because once you deploy the mock library, you cannot deploy the real library. Like they will conflict with each other because part of what the mock library does, it mocks Linux files. So as I showed, like we mock the /deb, right? Like, and once you are mocking /deb, if the real /deb is coming, there will be a conflict. So yeah, there is, the idea is to be on CPU only type of a scenario. And mostly because of we are mocking Linux files. So if a real GPU comes into play, Linux will try to create the real /deb files, and there will be a conflict. Mm-hmm. Yeah. Yeah, so it will fail inside the test kind node. Mm-hmm. Yeah, because everything is CDI based. So I used to, a couple of months ago, I changed teams, but I used to be a maintainer to the NVIDIA Container Toolkit. So I was in charge of what gets injected into your pod. So I know like how the Container Toolkit works. So that's why I created this library, because I know how we read the node and how we inject things in the pod. So having that knowledge allowed me to create the entire system. Yes. Yeah, we are now working in network stuff and in errors because we have been getting a lot of requests from customers on They want to fake errors and also internal customers at NVIDIA. We need to be able to fake that 2 or 3 nodes went down, and how are we responding to that? So that is still, there are some functionalities there, but we want to put like more effort into faking errors into the system. We have like 3 minutes, if not. Okay, thank you.